Good afternoon, everyone. This is Surendra Kumar Sharma, and I'm scientist at URC department at IIRS Dehradun. I'm also course coordinator of this 5 days training program on applications of machine learning in urban studies. Hope you people are enjoying the learning in this course. So, in today's lecture, we'll discuss about image classification and urban object or feature extraction using AI or ML techniques. So many of you must have heard about AI, ML, artificial intelligence, and machine learning techniques that are used for different applications in urban remote sensing. So here we will discuss about image classification and feature extraction. So first of all, introduction is about image classification. What is image classification? It is a process of categorizing or labeling pixels or regions in an image into different predefined classes. So here in this image classification, what we do, we take a single pixel of image or a collection of pixel or region of image and assign it to certain class, certain predefined class based on some spectral or special characteristics. Okay. So there are different steps that are involved in image classification. So first step is data acquisition. So in this step, you acquire the data, either we purchase or download satellite data, or we can also acquire ground data, UAV data, and many others. So then in next step, we do pre-processing. So some corrections, image enhancements are required many times, and image rectifications are required. So those pre-processing things we do in the second step. Then we go for the training data collection. So in this step, we select a certain number of pixels or certain number of regions in the image for each for different classes. For example, 5 classes are there, so we will select different number of pixels for each and every class. Okay. Then in next step, what we do, we select the classification algorithm, because this is very important step. In this, we have to select. There are numerous classification algorithms are available. So we have to select the classification algorithm that is suitable for our application. Okay, that is. So it depends upon many things. For example, what is our application, what level of accuracy our application require, what data types we have, what type of training data we have. For example, like deep learning models require huge data sets, okay? But the shallow neural networks require less data sets. So it also depends on how much training data set you have. Then it also depends upon what is your available computational power. So if you have huge data set and if you don't have computational power, you cannot use deep learning algorithms, because it will take several days to train the model. So once classification algorithm is selected, the next step is to train the model or algorithm on the training data. And then once it is trained, then we use either different parts of the image or the different image to classify using that trained model or trained algorithm. And in last step, we do post processing. So in post processing, what we do, so if our area is smaller, then it may be covered in a single image. But if our study area is larger one, for larger project, in that case, we can divide we can divide area into number of images, and then we do classification for each and every image, and then we mosaic all the classified outputs, and finally we do the accuracy assessment based on the ground truth we have available. So typically this is a classified image. This is first one is this is input image, and this is the classified image. This is how it looks like. Different classes are defined by the analyst or user who is using that algorithm. So the next comes the types of classification. So there are 3 types of classification. First one is manual or visual image interpretation. Second one is pixel-based classification, and third one is object-based or feature-based classification. So in manual classification, you must have heard about the visual image interpretation elements. There are 7 elements. In using those 7 elements, humans look at the image, and based on their expertise or based on these 7 image interpretation elements, they decide that this particular region or this particular pixel belongs to a particular class. So earlier this was the only way, because computers were not there. Then the, manual classification was the only way to classify the remote sensing image. So it works well for a small area, but if our area is larger one, then manual classification is tedious to do, and it takes a lot of time. The next is pixel-based classification. So in pixel-based classification, what we do, we choose one pixel and we assign this pixel to a already predefined class, and in this way, at the end, all the pixels are assigned to at least one class. And this assignment of this pixel to a certain class depends upon the spectral characteristics, and this is called the spectral pattern recognition. So the objective of pixel-based classification is to assign all the pixels in the image to a particular class or theme. It may be different class like built-up, forest, vegetation, agriculture. And the number of classes and type of class, these all are decided by the analyst, or it depends upon the for which application we need. So it totally depends upon us, who is doing the classification. Then next category comes object-based or feature-based classification. So earlier in pixel-based classification, what we were doing, we were using only spectral characteristics. But here in object-based classification, we use both the things, spectral as well as spatial information. Okay, so this step considers spectral characteristics, shape, texture, and spatial relationship with the surrounding pixels. So it considers the surrounding pixels also, not only that pixel that we are touching. So in object-based classification, it is a two-step process. In the first step, what we do, we segment the image into number of discrete objects or features, or we can say clusters. And then instead of assigning individual pixel to a class, we assign that individual object to a class. And this type of classification attempts to mimic the type of analysis done by the human during visual interpretation. So it is similar to the visual interpretation that is done by the humans. Then there are different image classification techniques. So you must have heard about these techniques: supervised classification, unsupervised classification, then semi-supervised classification. In supervised classification, what we do, we have input data and also we have the output data or labeled data. Okay, labeled image is there, and based on the labeled image, we tell the algorithm that for if this type of characteristic is special or spectral characteristic is there for this particular pixel or region, then it will belong to a particular class. It will belong to the built-up, or it will belong to the particular class vegetation. Okay, so input is there, output is there, and based on input and output availability, the algorithm learns if this type of scenario comes, then this will be the output. In unsupervised classification, we don't have label data or we don't have output. We just have input image, and based on its characteristics, the algorithm divides the image into different classes. Okay? Then third one is semi-supervised classification. This type of technique is used when we have limited number of label data. Okay, so we don't have what we say training data. Like we have a very small amount of training data. So in that case, what we do, first we do unsupervised classification. Then using the available labeled data, we refine that classified image in this semi-supervised algorithm. Then image classification. If you talk about the image classification algorithm, there are many image classification algorithms are available for remote sensing image classification. But commonly used algorithms are these: decision trees, random forest support vector machine, artificial neural network, or deep learning. Nowadays, deep learning is very popular in remote sensing, processing remote sensing data also. Then question comes, why we need image classification? What is the requirement? As you know that urban areas are growing at very fast rate. So in order to map urban area, or in order to take some decision, we need to extract some information. We need to prepare a map of the city. For example, you must have heard about that master plan formulation. Okay? So these things, for taking some decision by the authorities, we need to extract some information. So for that, we need image classification. So image classification is required in urban remote sensing for different applications such as land cover mapping that you must have heard about. Urban growth monitoring. In urban growth monitoring, what we do, we take the different timeline images, we classify the image, and we see how the particular urban area has grown in particular time period, and which class is converted to the which particular class. So this type analysis can be done. Then environmental monitoring. In environmental monitoring, what we do, for example, we want to analyze the green space of a city. So this type of study can also be done using the image classification. Then population estimation and socio-economic studies can also be done by the image classification. Then in this, we'll discuss about one demonstration. So here, what we did, many of you must have worked on the image classification in some commercial softwares like IIRS, IIRS, or some open source software like QGIS. But in this demo, we'll discuss about the image classification in Google Earth Engine. So many of you must have heard about the Google Earth Engine. It is a special data cube platform that is developed by Google. And in earlier methods, like you must have done in IIRS or ArcGIS or QGIS, you have to download the data and then you apply the classification algorithm, and then you classify the image. But here there is no need to download any data set. You just have to call the data set from the Google Earth Engine, and you just need a little bit understanding of programming. It may be either JavaScript or Python programming. So if you want to do coding in this Google Earth Engine platform itself, in that case, you need JavaScript. If you want to do in the Python, in that case, you can install it in your local system. So in this, what we did, we developed a user interface. Here, Landsat 8 image was taken, and the area was in Jaipur city, a small area in Jaipur city, and the image was 2022. And for demonstration purpose, we just have taken 3 algorithms: CART algorithm, random forest algorithm, and SPM algorithm. There are many algorithms are there, but you can select from those algorithms. But for demonstration purpose, we have selected only 3 algorithms. So you can see this is that GUI that we developed. Later on you can publish this GUI as a web application, and then anyone can access using that link. So then I will run this. So for this area, image is loaded. So this is 2-color composite of Landsat, and this is false color composite. Okay. So in this app, you just have to select which algorithm, using which algorithm you want to classify this algorithm, this image. So I have selected CART. So here you have to give the training samples also. Now in this demonstration, I am not selecting the training sample, but you can select from here that these are the options. This is point, line, polygon. This is rectangle. So I have already selected this built up and others in this. These are the built up points, and these are the other points. So I have taken just 2 classes, built up and non-built up. So in this way, you can select the different points, and you select the algorithm from here, CART, and when you click on this classify, it will classify on the fly. You can see this is our output. This red color is built up and white color is non-built up. You can check in this way also. Similarly, next algorithm can be selected like SPM. We'll click on SPM, and then we will click on the classify. So this is the classified output using SPM algorithm, and you can check it by unchecking this layer, classified image layer. Then next is random forest. We select a random forest and then we'll click on classify. So this is the result of random forest algorithm. Okay. So these are the results that we already seen: CART, algorithm, random forest, and SCM. So another case study, in this we will discuss about, we used OBIA, object-based image classification, so using UAV data. And in this, the study area was Lakshmi Narayan Institute of Technology, Nagpur, Maharashtra. And this is our study area, campus. In the whole campus, we have selected a small area. And this is our overall methodology: phase 1, phase 2, and phase 3. In phase 1, we have collected the UAV data, GCPs, and then we pre-processed the images, and then we generated DTM and DSM. And using DTM and DSM, we have obtained the NDSM. NDSM is nothing but normalized DSM, and we generate normalized DSM by just subtracting DTM from DSM, so that we can get the height of the features above, on the Earth surface. Okay. And then we generated the orthomosaic image. Using orthomosaic image and NDSM, they are taken as input for the next step, next phase. And in this stage, what we did first segmentation and then feature extraction. In segmentation, because we already discussed about object-based image classification. In object-based classification, what we do, we first segment image into the number of objects. Okay. So here we use multi-resolution segmentation algorithm, and then we use different features. And then using those features and those segments, we gave the training samples, and then we use different classification algorithm: K-nearest neighbor, random forest, decision tree, naive Bayes, and support vector machine analysis of the results. So in the first step, we captured 569 images, and 6 number of GCPs were collected. And these were our outputs: orthomosaic image and DSM. For the second step, second phase, segmentation and classification. So segmentation, this process is a trial and error method. So there is no hard and fast rule what should be the different other parameters like compactness. So we tried different things like scale. We taken 8, 25, 70 color piece values. So here the meaning of this one is color means and shape, they are interrelated. So if you give 0.8 value to the color, and that means you are giving more importance to the color feature of the image. And if you are taking it as a shape, a higher value, that means you are giving more importance to the shape. So by trial and error, we found out that this trial 3, we got the optimized values. So here then once the image is segmented, then we assign each segment to a particular class based on or knowledge. So this is training sample collection. Okay. So we assign using we assign the objects or feature to the different classes. Then these were the different features that were used. That means the meaning of this is based on these features, the particular object or feature will be assigned to a particular class. So what are the different available object features? These are the different available features, and we have selected mean from these layers. So what are these layers? Blue, green, red. These are the images because we have collected data in RGB, and then NDSM also we use. So mean value from these 4 layers, standard deviation from these 4 layers. And from the geometry feature, what we took area, border length, and width, and from shape we use compactness, roundedness, and rectangular fit. So there is no hard and fast rule what feature you should select. It depends upon your application. It depends upon your study area. So you can try different combinations and you check the accuracy. So these are the results obtained using random forest classifier. So you can see at certain area like here in this area, this is zebra crossing, but it is showing this sky color that is for the water bodies. So this was a misclassification using this random forest. Here also in in this area, this blue color is 2-story building and this red color is 3-story building. But here it is actually a tree, but it is again misclassified. This may be due to the DSM value. Tree may be at the same height as the building, so that's why this misclassification happened. And these results are obtained using the dysentery classifier algorithm. So if you we look at closely, you can see here this tree is there. Again, it was classified as a 2-story and 3-story building. And here you can see also this is water tank. So this is water body, and in between it is detected as a bare soil. And these are the results obtained using k-nearest neighbor algorithm. So you can see the tree is correctly classified, and here also there is no water body detected in using this algorithm. So this algorithm was giving better accuracy in comparison to all other algorithms. These are the results obtained using naive-based classifier. You can see again at zebra crossing it is showing water bodies, and here at tree also it is showing 2-story building. And at water body also there is one object, and it is showing a 2-story building. Then these are the results obtained using support vector machine. You can see here in zebra crossing it is showing water body, and here at tree it is showing a 3-story building. And you can see here at water body it is showing the 2-story building. And the overall accuracy that we assessed, so we found out that for different classes we got the we got that k-nearest was giving better result in comparison to all other algorithms. So there here one suggestion is there there is no hard and fast rule which particular algorithm you should use for your application or your study area, because it all depends on the study area for which you are doing study. So what type of accuracy, what level of accuracy you need, and which type of data set you are using, what type of training algorithms or training samples you are giving, training samples you are giving. So it all depends on these things. There is no hard and fast rule that this particular algorithm is best. Okay, so you can try different algorithms and then you can make a conclusion that for our data set or study area, this algorithm was best. So another case study that I have taken from the literature. So in this, that Sharma et al, what they did, they took the Landsat 8 images and they did the image classification, and they used ANN algorithm like shallow neural networks and deep neural networks also, and they found out that deep learning was far better in comparison to the traditional ANN algorithm. Okay. So, and this what they did, instead of taking single pixel, they divided image into the 5x5 tiles, and that 5x5 tile was assigned to a particular class, and that was processed as a input data. So the result shows that overall accuracy was 89.26%, and which was 11.52% higher in comparison to the traditional ANN algorithm. So you can see that deep learning is giving better results. In the later in this lecture, I will discuss when there is no hard and fast rule. There are some suggestions. In this case, that case you can use deep learning algorithm. Then next comes the feature extraction. And what is feature extraction? Object extraction or feature extraction, it is a process that involves identifying and delineating specific objects or features of interest within an image. Okay, so object or feature extraction from remote sensing imagery that can be used for different applications. For example, if I want to extract green spaces of particular city. Okay, so in that I just need to extract only the green space. So that may provide some valuable information to the authorities. They can decide that in this particular region of the city there is less green space, so we need to plant more trees, or we need to make different parks, green space parks. All these decisions can be taken. Or another example can be the smart trafficking. For smart trafficking, we need to extract the road infrastructure. Okay, so that decision can also be taken using the extracted features. So different types of urban features are there that can be extracted from remote sensing imagery. So some of them are buildings, roads and transportation infrastructure, vegetation and green spaces, water bodies, open spaces and public facilities, industrial areas, rooftop objects, and parking lots, and many more also there. Okay. Then question comes, why urban feature extraction? So urban feature extraction are used in various applications of urban remote sensing. So one is urban planning. So you must have heard about this master plan formation. So there in in order to prepare master plan, different layers are required. For example, building layers are required, road layer are required. So for that application, the feature extraction can be used. Infrastructure development, like government wants to develop some road infrastructure, so they need to first map the existing infrastructure, and then depending upon the requirement, they can propose at in this area new road infrastructure can be developed. Environmental application, it contains that, like green space extraction, then emergency response, like in the case of that. Many times we have seen that the ambulance or this fire brigade, they stuck in the traffic. So if we have in those type of scenario that if we have road network available with us, we can give them a alternate path. So in this type of urban applications, the urban feature extraction can be used. Then there are some government schemes and missions where also where that urban feature extraction can be used. One is smart city mission. Many of you must have heard about the smart city mission. The smart city mission is launched by Government of India. So the plan is to develop 100 smart cities. So in order to develop the smart city, different level of information is required. For example, smart parking. So for smart parking, first, what we need to do, we need to extract the parking spaces. So for that, feature extraction is required. And smart trafficking. In smart trafficking also, we need to extract different roads and transport networks that need to be extracted, and that can be utilized for taking the different decisions. Then second scheme is Amrut Atal Mission for Regeneration and Urban Transformation. So in this, there are different urban features that are required, such as roads, water supply, sewage networks, and drainage systems. The next scheme is Pradhan Mantri Awas Yojana. The aim of this scheme is to provide housing for all. So for that also, urban feature extraction helps to identifying the available places or location where the housing projects can be houses can be built, and assessing the availability of land and analyzing the existing housing stock. So where are different houses are there, those are allotted to the people. That can also be extracted using this urban feature extraction. Then next scheme is Swachh Bharat Mission. In this, like feature like public toilets can be extracted, and waste management facility and drainage system, that those can be extracted and then further analyzed where we need to install public toilets. All these things can be done. Then many others are the smart grid mission, national urban information systems, and there are many other schemes are also there where urban feature extraction can be helpful. Then there is another case study that we did. In this case study, we tried to extract built up using traditional artificial neural network, and the input was this Landsat 8 image. This is the Roorkee area, and this was the expected output, and this is how it will work. So we used Landsat 8 image, and the image was having 6 bands, band 2 to band 7 we considered for this study, built up extraction. And there were 2 classes, built up and non built up, and the input data was divided into 60/40 ratio. This was our input image, and this was our training label. And this was the architecture that we used So input layer contains 6 nodes because there are 6 number of bands for there in the image, and output layer contains 2 nodes because there are only 2 classes, built up and non-built up. And there was one hidden layer. It contains 18 nodes, and the activation function that we used was ReLU. And in final layer, there are 2 nodes, and activation function was the softmax. And the optimizer that we used was Adam, and model was trained for 5 POX. So again, there is no hard and fast rule see how much of hidden layers you should use, and how many number of nodes you should use in a particular layer. It is just randomly we select, and if our algorithm is giving better accuracy, we can change these things. Okay. Then for accuracy check, we use precision, recall, and SS score. So many of you must have must know these things, like precision is true positive divided by true positive plus false positive. So true positive is nothing but for example, in this case, true positive means built up was there and it was detected as a built up, and false positive means built up was not there but it was detected as a built up. Okay. Accuracy we achieved was for precision we got 0.815, recall we got 0.838, and FS score was 0.826. Then we did the same study, but this time we used the convolutional neural network or deep learning algorithm. In that we used the convolutional neural network. So again, same data set, Landsat 8, 6 bands, band 2 to band 7, and 2 classes output, built up and non-built up, and we divided the training data into 60-40 ratio for training and testing purpose. This was the same input and training label image. And here, instead of providing single pixel, what we did, we divided the image into 7 by 7 tiles. Because if we give the individual pixel, there will be no relationship with the surrounding. That means there will be no special relationship. So in order to get the special relationship, what we did, we divided the image into 7 by 7 tiles. So again, it is not fixed which size of tile you should use. You can use 3 by 3, 5 by 5, 7 by 7, 11 by 11. Depends upon the accuracy, what level of accuracy you achieve. So we tried with 3 by 3, 5 by 5, and 7 by 7, and we got the accuracy, better accuracy in 7 by 7 window. And the model architecture, again, the input layer is 6 nodes because there are 6 number of bands. Output layer is 6 because there are 2 number of nodes, and in between, like hidden layers, we use one convolution layer with 16 nodes, and ReLU was the activation function. Then second convolution layer with 32 nodes, ReLU was the activation function. Then third layer, 48 nodes, and ReLU was the function. And then dense layer, it contains 64 nodes, and ReLU, again, there is no hard and fast rule key how many number of layers you should use. And optimizer we used was Adam, and it was trained for the 5 POX. And you see the accuracy is improved. Now we got the precision as 0.931, R score 0.948, and F score is 0.938. Earlier it was around 8.3. You can see here. Around it earlier it was, and that using traditional ENL algorithm it was around 8.15 precision, and here we got 0.931. Then using this trained model, we applied on different city image. We used like Kashipur city in Uttarakhand, and the Landsat 8 satellite image was used, and we predicted using this trained model, and we got this type of output. Then in another case study, what we did, we used UAV data or aerial data, and using this aerial data, we tried to extract the building footprints using the deep learning algorithm. So this was our input, this is our deep learning model, and this is the expected output. So data set, we use publicly available data set downloaded from the internet. So the first data set was containing the images having resolution 224 by 224, and cross C, that means RGB images were there, and its corresponding mask or ground truth or labels were also available. For second data set, the resolution of image was 225 by 225, and again these images were RGB images. So you can see the size of both the data set have different dimensions of images. So in order to use the complete data set, we resized the second data set, and we resized all the images to 4 by 224 and converted these images into .png format. Then we splitted the data into 80% by 20% ratio for training and testing purpose. And then in the next step, we use data augmentation techniques. So many of you must have heard about this data augmentation technique. These techniques are used in order to increase the data size, because you know that deep learning algorithms require huge amount of data set. Okay, so in order to increase the size of the data, we use these data augmentation techniques. So data augmentation techniques are nothing but they just generate data from data. The meaning of this is, for example, we have used these techniques: image rotation, image flipping, noise injection, luminance change. So meaning of this is, for example, we have one input image and we rotated this image by 90 degrees. So we generated a second image. Similarly, we use image flipping. So in this case, for example, if we have 100 images, so we have generated 400 more images. So now we have 500 images instead of 100 images. So for this reason, data augmentation techniques are used in the deep learning. Then the model architecture that we used was unit architecture with ResNet 34 as encoder, and the learning rate that we used was 0.005. The optimizer was Adam, and it was trained for 150 epochs. Then for accuracy check, we use intersection over union. So intersection over union is nothing but the ratio of area of overlap divided by area of union. So for example, this is the ground truth or label, and this is the predictive one. So we'll overlay this, and we'll see the area of overlap between these two, and this divided by the union. So these are this is how the accuracy is checked. So this blue color is the ground truth, and this red color is the predicted one. So if this type of case occurs, then it is called the poor, and if this type of situation occurs, then it is called good, and if this type of overlapping is there, then it is called excellent, and the value should be near to 0.9264. And these are our predicted outputs, and we got the IOE value was 0.9109. That was very near to the excellent result. And then we use this trained model onto different data sets that were not present in our original training or testing data set. And you can see these buildings are extracted. These are the different buildings that are extracted here. Also in this also, these different buildings are extracted here also. In this image, there were no buildings, so it was not detected as building. Again, we applied on different data sets. So you can see the different buildings are extracted here. Another case study we did. In this case study, again we did building footprint extraction and 2D building chain detection using deep learning techniques. So here, first we extracted building footprints, and then we analyzed the chain detection. So we have taken the Chandigarh, the part of Chandigarh as our study area, and 3 timeline data sets were considered for 2003, 2012, and 2021. So for 2003, we used ICONOS data. For 2012, we used Pleiades 1A data, and for 2021, we used Google Earth satellite image data. And for building footprint extraction, we applied the building footprint extraction on the 2021 images. And the model architecture that we used was masked RCNN with ResNet 50 as backbone. And learning rate that we used was 0.0010964, and optimizer was Adam, and it was trained for 11 epochs. So these are the results that we obtained. So we divided our urban area into 3 types of urban density areas. One is high building density area. So then second one is medium density area, and third one is the low density area. So this is the high building density area. So you can see this is satellite image. These are the ground truth, and these are the extracted building footprints. and then we overlaid onto this, and we saw that these are the green color buildings are the buildings that are true positive. That means that buildings were there and they are detected as a building. And the overall accuracy that we achieved was 0.75, and that is considered as very good in case of the high density building areas. These are the results obtained for medium building density area. So this is the input image, these are ground truth, and these are extracted building footprints. So you can see there are very less number of false positives. These red colors are red false positives, and we achieved accuracy was 95.29%. So this is low building density area. So this is the input image. These are ground truth, and these are the extracted buildings. So you can see one very less number of buildings were detected as false positive. So the achieved accuracy was 98.85. Then in next step, these buildings were extracted on 2021 image, and the resolution was 2021 image was 40 centimeters. So we cannot apply the same algorithm onto the other images because other images had different resolutions. So in order to bring the resolution of those other timeline images to the same level as of 2021, we use super resolution techniques. In super, we use GAN architecture, generative adversarial network, in which there are two things. One is generator, second one is there are two components in the GAN architecture. One is generator, second is discriminator. So generator was taken as UNet, and discriminator was taken as VGC16, and the learning parameter was same as earlier one, and Adam optimizer used, and it was trained for 18 epochs. And then using this trained network, we brought the resolution of those 2003 and 2012 images to the same as the 2021 images. And then we applied the building footprint extraction algorithm that we trained to the those 2003 and 2012 super resolved images also. And then we analyze the change detection. So you can see this is from 2003 to 2012 change detection. These yellow color buildings are the no change building. That means they were present in 2003 also and 2012 also. These purple color buildings are those buildings are which are newly constructed. Okay. And these green color buildings are those buildings that were present in 2003 but were demolished in 2012. So these areas here. Okay. Then this is the change detection from 2012 to 2021. So again, these yellow color buildings are those buildings but no change. These are newly constructed areas, and these green areas are the demolished one. Okay, and this is the complete one from 2003 to 2012 and 2021 images. Then one more case study that we did was for Kashi Vishwanath temple area. So many of you must have heard that the Kashi Vishwanath temple corridor was developed, and that was inaugurated by Honorable Prime Minister in December 2021. So here what we did, we analyzed the different timeline images from May 2018 to December 2021, and we used same algorithm that we used for building footprint extraction in case of Chandigarh area. So mask RCN with ResNet 50 as backbone. Learning parameter was same, and then Adam optimizer was used, and it was trained for 11 epochs. Okay. And this is the May 2018 image. This is the image, satellite image, and this is the extracted building. Then in March 2019, the demolition started. So this is the area, and this is the extracted building. This is the area in 2019, and the extracted building. Then 2020, then extracted building in 2020. So you can see the construction has already started. And then March 2021, some buildings are appearing. And then finally December 2021. Okay. And then we saw the change, analyze the change detection. So from 2018 to 2021. So all these green color buildings are the unchanged buildings. That means those buildings were present in 2018 and 2021 also. And these red color buildings were those buildings that were demolished or dismantled, And these blue color buildings are those buildings that were newly constructed. So you can see this is the area where temple is there, and from this area to this area there is a complete corridor is there. So pilgrims can move from this this temple to the ghat. Okay, thank you. That's all from my side. If time permits, we can take some questions. So if your questions are not answered today, you can you can contact me through the social media accounts like LinkedIn, ResearchGate, Facebook, or Twitter. Okay. Thank you.